Hello everyone, this is lecture 7, dot product. So far we talked about different vector operations including scalar multiplications, vector additions, and vector subtractions. However, we haven't talked about the product between two vectors. Actually, there are two types of products between two vectors. The first one is the dot product that we're going to cover in this lecture, and the second type is the cross product, which we will cover in lecture 8. So hopefully at the end of this lecture, we could be able to calculate the dot product of two given vectors, and you could be able to determine whether the two given vectors are orthogonal. So orthogonal is the definition of perpendicular. So we want to know if two vectors are perpendicular with one another or not. And later on, hopefully we could be able to explain what is meant by the vector projections of one vector onto another vector and learn how to calculate it. The dot product is used to determine the angle between two vectors. It is also a tool for calculating projections, again, which we're going to learn later, to measure how much of a given vector lies in the directions of another vector. So there's a lot of geometric applications of the dot product. So it is useful to learn about the dot product. So first, the definitions and about the properties of the dot product. So definitions, the dot product, there's another name for that, it's called a scalar product. So the dot product between two three-dimensional vector is given by the sum of the products of the components. That is, you have u dot with v is equal to u1 v1 plus u2 v2 plus u3 v3. And later on, I'm going to show you the proof to show that where this calculation is actually coming from. But for now, please accept the formula. Just use the formula to calculate the dot product between two vectors. So this formula can be, of course, write in form of the two-dimensional vectors. Right? So if you have two-dimensional vectors, u equal to u1, u2, and v is equal to v1, v2, the calculations can also give you u dot with v equal to u1 v1 plus u2 v2. And as a matter of fact, you can extend these calculations to any dimensions. So the calculation is going to give you a constant or a scalar. So that's why the dot product also has the name the scalar product. Next, let's do the following example. We would like to calculate the dot product of the two vectors u equal to 3, 5, 2 and v is equal to negative 1, 3, 0. This should be a very straightforward calculation. So you get u dot with v. Now from now on, I will be very specific with the notations in terms of what is the dot product, what is the regular multiplication. Sometimes I use dot for the regular multiplications, but very specific case, and it just when I just want to make sure that is a regular multiplication, I will mention it. Okay, but most of the time when I use the dot between the two vectors, that means it's the dot product. So u dot with v, this is equivalent to the vector 3, 5, 2 dot with negative 1, 3, 0. When you apply the formula, you get 3 times negative 1 plus 5 times 3 plus 2 times 0. And you get negative 3 plus 15 equal to 12. And this result is positive. So it means something here later when you get to the geometric meaning of the dot product. Okay, so just bear with me here. This is just the calculation and you get positive 12, which is a constant or a scalar. And again, because of that, you have the dot product to be a scalar product. Now in the next example, you have two three-dimensional vectors. U is equal to 10, -4, and 7, and V is equal to -2, 1, and 6. When you do the dot product between these two vectors, you get to do 10, -4, 7, dot with -2, 1, 6. So now you get 10 times -2 plus -4 times 1 plus 7 times 6. Then you get -20 minus 4 plus 42. And if you do the calculations correctly, you get 18 for the answer. Again, the dot product gives you a positive number or positive scalar, and it means something a little bit later. So there are some properties of the dot product that you may want to know. Now let's say you have three different vectors, u, v, and w, and a scalar, which is alpha in this case. There are four properties that you want to know, but technically there are a lot more properties related to dot product, but for the basic properties of the dot product, you have the four properties here. So the first one is the commutative property. That means if you do the dot product of u dot with v, this is equivalent to doing v dot with u. They both give you the same scalar at the end. Distributive property is the second property here. If you have three different vectors, you have u dot with v plus w. This is equal to u dot with vector v plus u dot with vector w. The next property is the associative property of a scalar. So it say that if you have the two vectors u and v, and you will form the dot product between the two vectors, then you scale the result. It's going to be equivalent to doing a scale of vector u first, and then the resulting vector dot with vector v, or this is equivalent to vector u dot with alpha of vector v. So it say that if you scale vector v first, and then the resulting vector get dotted with vector u, okay, they're going to be the same with these two results. The last one is quite important, which is the property of magnitude. So the magnitude of u squared is equal to u dot with itself. Or of course, when you do the magnitude of vector v squared, this is equal to vector v dot with itself. So armed with these properties, we're going to go to example 2. Now you have three vectors a, b, and c. They are three-dimensional vectors. Let's do the first calculations here. So you have a dot with b and then multiply with c. So in this case, this multiplication is just the regular multiplications. This one right here in the parentheses is the dot product. Whatever you get for the dot product, you multiply or apply the regular multiplications to vector c. So first, a dot with b, right, you get the vector 1, 2, -3, dot with vector 0, 2, 4, and then you're going to multiply with vector c, 5, -1, 3. So inside the parenthesis, you get the dot product, and you get 1 times 0 plus 2 times 2 plus -3 times 4, multiply with 5, -1, 3. So this gives you 4 minus 12 times 5, comma -1, 3, or -8 times 5, -1, 3. If you distribute -8 into every term inside a vector, we get this -40, positive a, -24. Now next we do a dot with 2c. So you're going to scale the vector c first and then apply the dot product for a and the resulting vector of 2c. So a again is equal to 1 to -3. You dot with 2 times vector c, which is 5, negative 1, 3. So you have 1, 2, negative 3, that with 10, negative 2, 6. What is 1 times 10 plus 2 times negative 2 plus negative 3 times 6. You get 10 minus 4 minus 18. And if you do the calculations correctly, you get negative 12. And the last practice is the magnitude of b squared, or this can be written as the magnitude of b squared with the two vertical lines each side of vector b. So we're going to apply the fourth properties of the dot product, which is property of magnitude. Is say that the magnitude of u squared is going to be equal to u dot with itself. So in this case, the magnitude of b squared give you the dot product of b with itself, or 0 to 4 dot with itself 0 to 4. And you get 0 squared plus 2 squared plus 4 squared, and the result is 20. Because of this calculation, you see that when written in the component form, the magnitude of b squared, or the magnitude of a vector square, give you the result of u1 squared plus u2 squared plus u3 squared. Or if you have the magnitude of the vector v squared, this gives you v1 squared plus v2 squared plus v3 squared. Given vector u and vector v are three-dimensional vectors, and technically you can apply to the two-dimensional case or four-dimensional case, five-dimensional case, or in general n-dimensional case. So that is, if you have u equal to u1, u2, the magnitude of u squared is u1 squared plus u2 squared. I hope that helped. Now we're going to move on to the next topic, which is the geometric interpretations of the dot product. Okay, so if you have the two vectors in these positions, right, they have the tails attached to one another, and the two vectors form an angle, and this angle is theta. So if theta is the angle between u and v, then the dot product u dot with v is equal to the magnitude of u times the magnitude of v times cosine of the angle between the two vectors. From here, you can actually calculate the angle between the two vectors by solving for cosine of theta. Here you get cosine of theta equal to u dot with v altogether divided by the magnitude of u times the magnitude of v. So in this case, theta is the angle between u and v. And we also make a very important assumption that we're going to consider theta to be between 0 and pi only, with theta is between 0 and pi. Because we want to just identify the angle between the two vectors in terms of acute angle, orthogonal vectors, 90-degree angle, or obtuse angle. And from here, I'm going to show you the proof, not the proof of cosine, but the proof of how we get the formula to calculate the dot product between the two vectors. The formula is u1 times v1 plus u2 times v2 plus u3 times v3. Okay, so here's the proof for the dot product given two three-dimensional vectors. So here we're going to consider two position vector u equal to u1, u2, and u3, and v is equal to v1, v2, v3. And suppose theta is the angle between the two vectors. So in this case, this is an example of two vectors. So the two vectors are placed in this particular positions, and theta is the angle between the two vectors. And suppose theta is the angle between the two vectors. Then you have, by placing the two vectors u and v in this particular positions, you have the third vector, which is the vector difference. So the vector u minus v form the third side of a triangle. So from this setup, I'm going to show you how to get the formula for the dot product. That is u dot with v equal to u1 times v1 plus u2 times v2 plus u3 times v3. So first of all, by the law of cosine, so given the triangle, a generic triangle, the law of cosine gives you the information that c squared equal to a squared plus b squared minus 2 times a times b times cosine of theta. So this is the law of cosine for a generic triangle. Now we're going to apply the law of cosine for this particular triangle. So by the law of cosine, you get that the magnitude of u minus v squared is equal to the magnitude of u squared plus the magnitude of v squared minus 2 times the magnitude of u times the magnitude of v times cosine of theta. Then by the geometric definitions of the dot product, this term right here, magnitude of u times the magnitude of v times cosine of theta, is going to be the dot product u dot with v. Then we could be able to rewrite the equations as follow. You have the magnitude of u minus v altogether square equal to the magnitude of u square plus the magnitude of v square minus 2 times u dot with v. Then from here you can solve the dot product as follow. You get u dot with v equal to 1/2 times the magnitude of u square plus the magnitude of v square minus the magnitude of u minus v altogether square. Then we're going to use the definitions of magnitude which we learned before. So by the definitions of magnitude, we get that the magnitude of u is equal to the square root of u1 squared plus u2 squared plus u3 squared, or the magnitude of u squared give us u1 squared plus u2 squared plus u3 squared. And similarly, we're going to get vector v, the magnitude of vector v squared is v1 squared plus v2 squared plus v3 squared. And when you calculate the vector u minus v, you're going to get u1 minus v1, comma u2 minus v2, comma u3 minus v3. And when you take the magnitude of this and square the difference, you're going to get u1 minus v1 square plus u2 minus v2 square plus u3 minus v3 square. And then with this calculations of the magnitude of u squared, the magnitude of v squared, and the magnitude of the difference square, you substitute back into this equation. So I'm gonna call this equation star. So substitute this calculations into star or equation star. We obtain, so you get u dot with v equal to 1/2 times u1 square plus u2 square plus u3 square plus v1 square plus v2 square plus v3 square minus u1 minus v1 square minus u2 minus v2 square, and then minus u3 minus v3 square. And then you're going to expand this expressions. Okay, and we're going to get 1/2 times u1 square plus u2 square plus u3 square plus v1 square plus v2 square plus v3 square minus u1 square minus 2u1 v1 plus v1 square, then minus u2 square minus 2u2 v2 plus v2 square, then minus u3 square minus 2u3 v3 plus v3 square. Next, we're going to distribute negative into the parentheses, and you get 1/2 times u1 square plus u2 square plus u3 square plus v1 square plus v2 square plus v3 square minus u1 square plus 2u1 v1 minus v1 square minus v2 square plus 2u2 v2 minus v2 square. And then for the last expressions, you get minus u3 square plus 2u3 v3 minus v3 square. Now, after these calculations, we're going to simplify or combine like terms for that matter. We see that u1 square cancel out with u1 square here. So positive u1 square minus u1 square, and so on and so forth. So u2 square and negative u2 square, u3 square minus u3 square, v1 square, negative v1 square, v2 square, and negative v2 square, v3 square, and negative v3 square. And technically, we left with just 2 times u1 v1 plus 2u2 v2 and plus 2 times u3 v3. So you got u dot with v now equal to 1/2 times 2u1 v1 plus 2u2 v2 plus 2u3 v3. And 2 is the common factor inside the parentheses, so you take out the 2 and the 2 with the 1/2 in front going to cancel out, and you're left with u dot with v equal to u1 v1 plus u2 v2 plus u3 v3. So technically this is the proof to show the calculations of u dot with v. Right. Again, u dot with v is equal to u1 times v1 plus u2 times v2 plus u3 times v3. Now, using the formula of geometric interpretations of the dot product, you can calculate or you can determine the angle between the two vectors. And one of the application of the formula cosine of theta equal to u dot with v over the magnitude of u times the magnitude of v is for us to determine if the two vectors are orthogonal to one another. So the idea of orthogonal vector is that we want to know if the two vectors form a 90-degree angle or not, or if they are perpendicular to one another or not. So the two non-zero vector u and v are orthogonal if and only if the dot product between the two vectors equal to 0. So this is a scalar 0. If u dot with v equal to 0, then the two vectors are orthogonal or perpendicular to one another, or they form a 90-degree angle. So I'm going to give you the proof of this particular theorem. So this theorem is an if and only if statement, so there are two directions to the proof. So first we assume there are two non-zero vector and they are orthogonal to one another. Again, the orthogonal idea is the two vectors are perpendicular or they form a 90-degree angle. And with that assumption, we're going to show that u dot with v is equal to 0. For the reverse direction, when you assume that u dot with v equal to 0, and then you can calculate the angle between the two vectors, and then we can say that the two vectors are orthogonal to one another. So first, you're going to let u and v be non-zero vector. And suppose theta is the angle between u and v. First, we assume that u and v are orthogonal, or the angle between the two vectors are pi over 2 or 90-degree angle. Then you do the calculations of the dot product, that is u dot with v equal to the magnitude of u times the magnitude of v times cosine of theta, which is the angle between the two vectors. But in this case, theta is equal to pi over 2 or 90-degree angle. So therefore, you get the magnitude of u times the magnitude of v times cosine of pi over 2, and cosine of pi over 2 is equal to 0. Therefore, the dot product is equal to 0. Now we're gonna go in the reverse directions by first assume that u dot with v is equal to 0. So conversely, we assume that u dot with v is equal to 0. Then you have that cosine of theta is equal to u dot with v divided by the magnitude of u times the magnitude of v. But we assume that u dot with v is equal to 0, so 0 divided by the magnitude of u and the magnitude of v is going to give you 0. So when cosine of theta equal to 0, I'm just going to take the value of theta equal to 0. Without any assumptions, you can choose the value of theta to be 90-degree angle or 270-degree angle, so on and so forth. But we make the assumptions earlier that theta in this context is always between 0 and pi. So therefore, cosine of theta equal to 0 implies that theta is equal to pi over 2 or 90-degree angle. Then you have theta equal to 90-degree angle or pi over 2, implying that u and v are orthogonal. Right. So with this information, let's apply it to example 3. You have two three-dimensional vectors and we want to know if they are orthogonal to one another. So by doing the calculations that u dot with v equal to 1, 0, 5, dot width 10, 3, negative 2. So here you apply the dot product of two vectors and you get 1 times 10 plus 0 times 3 plus 5 times negative 2. And obviously the answer is 0, so you conclude that the vectors u and v are orthogonal. Now let's continue with example 4. In this example, you have three-dimensional vectors. And first, let's compute the dot product of u dot with v. So part A, you got u dot with v, and this gives you root 3, 1, 0, dot with 1, root 3, 0, or root 3 times 1 plus 1 times root 3 plus 0 times 0, and you get 2 times root 3 for the results. Now we're going to find the angle between the two vectors u and v using the formula that cosine of theta, which would be the angle between the two vectors u and v, is equal to u dot with v divided by the magnitude of u times the magnitude of v. So u dot with v we got right here, which is 2 times root 3, altogether divided by the magnitude of u, which is square root of root 3 square plus 1 square plus 0 square, so I'm just going to ignore it, times the square root of, or the magnitude of v, which is square root of 1 square plus root 3 square. And the numerator, you got 2 times root 3. In the denominator, you see that root 3 square is 3 plus 1 is 4, so square root of 4 is 2 times 2. So cosine of theta is 2 times root 3 over 4. Well, this is root 3 over 2. So theta is equal to our cosine of root 3 over 2, which is equal to pi over 6, or 30-degree angle. We just have the pi over 6 value, or 30-degree angle, because the assumptions for theta, or the angle between the two vectors, is that theta is between 0 and pi only, where theta is the angle between u and v, and theta is between 0 and pi only. Now for part C, we want to calculate the angle between u and w. So I'm going to do a few calculations first before I jump into part C. So the first calculations is u dot with w. So u dot with w is root 3, 1, 0 dot with 1, root 3, 2 times root 3. If you do the calculations correct, 2 times root 3. And the magnitude of u going to give the answer of 2. The magnitude of w going to give the answer of 4. And then with this information, I'm going to calculate the angle between u and w. So assume that I have an angle, let's say alpha is the angle between the two vectors u and w. So C is cosine of alpha equal to u dot with w divided by the magnitude of u times the magnitude of w. So u dot with w we calculated earlier here, which is 2 times root 3. divided by the magnitude of u, which is 2, times 4, well, you have root 3 over 4. Unfortunately, cosine of alpha equal to root 3 over 4 does not give you any special angle that you would like, but certainly we can use a calculator for this. So alpha is equal to arc cosine of root 3 over 4. If you use a calculator, you're going to get this going to be 1.12 radian, or it's equal to 64.3 degree angle.